Before we can talk about the second shifting theorem, we need to discuss a function called the Heaviside function. And here is a picture of the really jovial looking Oliver Heaviside, who has one of my favorite quotes about mathematics ever. He said, "Mathematics is an experimental science. The definitions do not come first, but later on." And what I love about that quote so much is the function that we're going to use, called the Heaviside function, or your textbook calls it the unit step function, is absolutely a result of something like this. So here's what I'm talking about. I'm going to show the definition here. So the definition of the Heaviside, or the unit step function, comes from a need for having a function that turns graphs off and on, turns functions off and on. So having it like an intermittent, let's say, forcing function. So here's what this graph does. I'm going to graph it first. The graph of the basic unit step function looks like this. From 0 to a, the graph is at 0. At a, the graph jumps up to 1, and it's just equal to y equals 1 or f equals 1 from 1 to infinity. And here's how we would write this function. The unit step function with u sub a is a piecewise function where it's equal to 0 for t is between 0 and a, equal to 0 but not to a. So it's right side equality. And the unit step function is equal to 1 where t is greater than or equal to a. So going back to the idea of intermittent, this graph is off, if you'll accept that vernacular. It's off from 0 to a, and then a light switches on, and it turns on with the most basic function of all, 1, at a. Okay, so let me show you what we're going to expand this so it's a little bit more complicated and helps us with our much more complicated functions. But what's cool about this is this function, just like he said to here, came from a need for a definition. So we made one up. It's so true in mathematics. It's so true. Okay, let's do an example. So for this first example, I'm still going to keep our function pretty simplistic, and I just want us to sketch what this function might look like. F of t equals u sub 3 of t minus u sub 5 of t, where u is the unit step function or the Heaviside function. Okay, let's talk about what this is. So the first thing I'm going to do before I sketch this is I'm going to write this in piecewise notation, going off of this. So u sub 3 means that the graph is equal to 0 from t going, a has to be positive for this. So it has to be equal to 0 for t between 0 and 3, and then it's 1 for t is greater than or equal to 3. That's from our first part. The second part, u of 5, says that we have to have it 0 up until 5, so that won't affect any of this stuff. And then at 5, t is greater than or equal to 5, we have our original function 1 minus u of 5. Oh, that's just going to give us as 0. Okay. So here's what, I don't like the way that's written. I'm going to rewrite f of t. It's all correct. I just don't like the way it's written. So we've got 0 from t is between 0 and 3, inclusive on the left. We've got 1, but then we've got 0 again. So we've only got it equal to 1 for t is between 3 and 5. So 3 is less than or equal to t, which is less than 5, and then t is greater than or equal to 5. 1 minus 1, or this unit step function minus this unit step function, is 0. So let me draw a picture of it, because that was what it said to do. Okay, so I have from 0 to 3, I have 0. No disagreement there. From 3 to 5, I have 1. But from 5 on, I have 1 minus 1. So I have 0 again. So here's how I want you to think of the unit step function. I'm going to go to red. This part here, u3 of t, turns y equals 1 on at t equals 3. And this minus u sub 5 of t turns y equals 1 off, or back to 0, at t equals 5. Okay. The 1 you can see in the statement of the f of t if you think of it as like a coefficient. So let me translate this again. F of t equals u sub 3 minus u sub 5 means turn on 1 at t equals 3, turn on the function 1 at t equals 3, and then turn it off at t equals 5 because you're subtracting. Okay. I want to try that with a more complicated looking function. So our only goal for this first example was just to sketch it. So let's try it with a more complicated looking function. Let me scroll up here and let's try it with this. Let's rewrite f of t is equal to the following piecewise function, and I'm going to be mean. I want 4 pieces. 0, 1, t squared, t cubed. Now I want this equal to 0 when t is between 0 and 1. I want the function equal to 1 when t is between 1 and 2. I want it equal to t squared when t is between 2 and 3. And I want it equal to t cubed when t is bigger than or equal to 3. And all of my compound inequalities, they're all equals on the left side, not on the right side. So what we're going to be able to do is we're going to be able to rewrite these piecewise functions or intermittent functions as a Heaviside function instead. So here's how I'm going to do this. Rewrite this f of t as a unit step function. Okay, so here we go. First, I want to turn on the function 1 at t equals 1. So I'm going to take off the u of t's. I'm just going to write u. So to turn on the function 1 at 1, I'm going to write 1 times u sub 1. Then I want to turn off the function 1 at t equals 2, so minus 1 times u2. So this turns y equals 1 on at t equals 1 and off at t equals 2. u1 minus u2. Okay, now I want to turn the function t squared on at t equals 2 and off at t equals 3. So here's how I'm going to write that. Plus t squared u2. Positive will turn that function t squared on at u2. Oh, I wish I had written this t squared in red, because that's the function I'm turning on and off. And then I want to turn that function off, minus t squared at u3. So this second part, this turns y equals t squared on at t equals 2 and off at t equals 3. And then finally, I want to turn on, so plus the function t cubed at t equals 3, and I want to just keep it on. So plus t cubed u3. This turns y equals t cubed on at t equals 3, and it stays on. Okay. So u1 minus u2 turns the function 1 on at 1 and off at 2. T squared u2 minus t squared u3 turns the function t squared on at u2 and off at u3. And plus t cubed u3 turns the function on at u3. For Laplace transform purposes, it will be beneficial to combine all of your u sub i's together. So that will look like this. F of t equals u1. There are no other u1s. But for u2, we had a t squared and a minus 1. The u2s, we had a t squared and a minus 1. So I'll factor out the u2 and write t squared and minus 1. And at the u3s, I have a t cubed and a minus t squared. So plus u3, I have a t cubed and a minus t squared. So for Laplace transform purposes, both are equivalent, but the second one that we just wrote is better. So let me translate this into English. This means at t equals 1, turn on y equals 1. Next, at u2, at t equals 2, turn on y equals t squared and y equals 1 off. Turn at u2, at time equals 2, turn t squared on and 1 off. And at time equals 3, turn t cubed on and t squared off. At t equals 3, turn t cubed on and y equals t squared off. So that's what that means in English. Let me show you a picture of that. If you were to graph the piecewise function f of t, which you should be able to do no problem. It's a pretty simple piecewise function. If you were to graph it, we have all of these things happening in that graph. So here's what that graph would look like. So notice for the graph of this piecewise function, we have nothing from 0 to 1. Then at 1, we turn on t equals 1. At 2, we turn off t equals 1 and we turn on the t squared. At 3, we turn off the t squared and then we continue on with t cubed forever and always. So our graph reflects our Heaviside function interpretation. Okay, 10.6 is a quick section. It's a quick section. It's just getting you used to this rather strange but oh so helpful function.